Okay, let's get started. We're doing this is number 26 video, and we're doing the assignments that I gave you yesterday. There were 7 altogether, but this video will do the first 5, which are considered the doable ones, the easy ones, the ones that you should be able to do. As I mentioned in my letter this morning, I'll send you more like this, but you're expected to be able to do it. You'll be tested on it. Okay. So question number 1 is asking you to find the volume of a cone here. You should understand by now that C refers to the circumference and H, of course, is the height. So yet again, I'll do this again. You have to understand it. It's 8th grade math. So here we go again. We know that C equals 2 pi r. And we know that C equals 16 pi. So it follows instantly that 16 pi equals 2 pi r. When I divide both sides by 2 pi r, the answer is instant. R equals 8. Well, once I get over that part, I'm easily able to solve the rest of the problem. R equals 8, therefore, 1/3 pi 8 squared times 6, canceling immediately, and 8 squared times 2 times pi, and I'll let you do that. You should have been able to do it easily, and the answer, of course, is 128 pi. Obviously, the answer is in terms of pi. You're expected to be able to do a simple problem like that. You'll get more, but by now, I'll be turning my attention to calculators and radicals when we do some of these problems. Okay, so that's over with, and we erase all the data and we move on to number 2. And in number 2, again, we're watching carefully. We know that the radius is 5, the slant is 13. Oh my God, it has to be that famous triple, the 5, 12, 13 Pythagorean right triangle. You're responsible for doing simple work like that. So now I know what R is. R is 5, and now I know what H is. I meant to say H is 12. Okay, so there we go. You're expected to do that. It's a very reasonable assumption that you could do that. It's a cone again, so we go 1/3 pi 5 squared for the R, and 12 for the H. Well, isn't that nice? 12 is a multiple of 3, and then 5 squared is 25, and 25 times 4 is 100, and you should have easily, if you saw the triple there, be able to come up with 100 pi without the need of a calculator. Okay, moving on. We go to problem number 3. And in problem number 3, this time we're giving a cylinder. And we look for the data. Nothing happens without a data. Oh, just like yesterday. A, you should understand perfectly, is the area. Okay? And the area is 121 pi. Isn't that so nice that 121 is a perfect square? And they give you here a little picture of the 10 here for the height, and there you go. You're in great shape. If A equals 121 pi, and at the same time A equals pi r squared, then it follows instantly that pi r squared equals 121 pi, and I can just cancel with mental math, or you could divide both sides by pi, but you need to recognize at your age that 121 is a perfect square, and perfect square of 121, the perfect number, the radical is 11. You should know that. Shouldn't be a big deal. So here we go again. R equals 11, and now we just plug in our formula. Pi, no 1/3 this time, obviously, it's a cylinder. 11 squared times 10, and there's going to be the answer. And when you work that out on the calculator, at least that's what I got, 121 times 10, I just added a 0, as we learned in scientific notation. Tag along the pi because everything's in terms of pi, so we can do the math easily, and the answer's there. Okay? All right? And look at the thing. Okay, we're only at 5, so we're in good shape to do number 6. With 5 minutes, we're in good shape to do number 4. Flip the page. Make sure we're not making any mistakes. And this time, it says, how many cups does this water dispensary contain? So maybe they're asking you to think backwards here. But, you've seen in the offices where they have this little pipe coming out, and you put the cup underneath the pipe, and the water comes down. And the question would be, if the diameter here is 24, the height is 10. We'll change this today into real-life problems. And the diameter here is 6. And the height, not the slant, is 5, then we're concerned about finding how many cups will go into the, how many cups the water dispenser will actually dispense. And this could be an engineering problem. No concerns whatsoever. Surely you've seen these water dispensers in the office, and most of the water cups or plastic cups are in the shape of a cone. So here we go. It's best to put the dispensary on the top and the cups on the bottom. And once I can find the ratio between those two guys, then I'll be in great shape. So again, going left to right, the cylinder has a volume of pi, and half of 24 is 12. You should see that easily. I repeat the 12 again because it's squared, and then I'm working on the 10, which is the height, and I'm going to divide that by 1 cup, and then I'll know the ratio, and I'll know the number of cups that this dispensary gives me. And I go on the bottom here, and it's 1/3 pi. Half of 6 is 3, so that's 3 times 3. You see, since we've done it so many times, the height being 5, I'm in great shape to do the problem. There's the pi, which I left out. So I rewrite what I have left here, and I'll easily be able to come up with an answer. So pi times 12 times 12 times 10 divided by pi times 3 times 5. It's getting easier and easier to do this kind of math. We get 8 times 12. That's all that's left when I do the canceling. So without any pain whatsoever, I come up with 96 over 1, which translates in this problem to 96 cups, this dispensary, with the water, with the dimensions that we've been giving in units, not in real world numbers. Like I said before, we'll get to that. Okay, so there we've given the answers for the first 4, and now we'll go to number 5. By the way, that was number 4. Again, I'm working on making sure that everybody understands what I'm doing here, trying anyway. And now we go to the next problem, number 5, and let's take a look at that. It's strictly a word problem, so I'll read it out loud instead of, since you have the word problem in front of you. It says, find the ratio of a sphere, radius 3, and to a new sphere, where the radius has been tripled. So if I'm got my math down right, triple means 3, so 3 times 3 means r equals 9. That's kind of an interesting problem. Here, let's make this sphere a little bigger so we can get an idea of what's going on here. Well, that's kind of an interesting thought, what's going on here. What does happen? Obviously, well, maybe it's not so obvious. All spheres are similar. You just change the radius, and here, when I say triple, I'm just increasing it by scale factor 3. You should think about that for a minute. So what happens when we're asking the relation of the volume of the new guy really, if you think about it, the guy that's been extended, the guy that's been, to use our vocabulary, dilated by scale factor 3 to the original. And that's all the problem's asking you. I'll give you another one today so you can think about that. But if you really get down and thinking hard, all spheres must be similar. All circles must be similar. All squares must be similar. I can only change them by multiplying by a scale factor. We'll talk more about that later. It comes up in the Regents exam. Okay, so now what's the new? Well, it's 4 over 3 pi 9 cubed, right? Because as we know, the spheres don't have any height. A circle doesn't either, if you think about it. And divided by 4 over 3 pi 3 cubed. Well, any number cancels itself when they're the same number, so we don't have to waste time twisting around in the air like a pretzel doing all this algebra. So what we have is 9 cubed divided by 3 cubed. But if you do the math, just stop. 3 times 3 times 3 is 3 cubed. And of course, that's 27. Oh, that's very interesting. It seems to be telling us that that when you know the radius of a smaller figure and you increase and decrease it or dilate it, and by a factor of 3, then it's going to be 3 cubed. It's going to end up to be 3 cubed times what you had there. Very interesting, a 27 to 1 ratio. So your new balloon, if you like, you're popping up a balloon, is 20 times the size, 27 times the size in volume as the old one. Okay, we're reaching our time limit here. Let's just turn this off.